Second big myth. Ready? Let's go on. Gas migration from faulty wells is a rare phenomenon. I smell Duke. All right, what's the element of truth here in this myth? What's rare? What does it mean to say something is rare? Uncommon, not usually expected, not likely to occur every time something happens, rare. Okay? So let's talk about what gas migration looks like and sounds like. You're not going to be able to hear it from these tinny speakers, but you'll be able to see it. How many people have seen this video? Nobody else has seen this video? Okay. Anybody recognize any of the hardware in this video? Do you know what this is? It's a wellhead. This is the production casing coming up out of the ground through the cellar. And the bubbling, what's that? It's gas. Where's the gas supposed to be coming? Inside. Why is it coming outside? Oh, lots of reasons possible, and we're going to investigate some of those. So this is a well that's still bubbling in Pennsylvania. It's been bubbling for about a year and a half. So it's producing gas through its riser, but it's also producing gas through a faulty execution. This is not a well with structural integrity. That's what gas migration looks like. So I'm going to use some cartoons generated by Southwest Natural Gas. These were PowerPoint slides that were presented at a recent EPA workshop in Washington, D.C. that I was invited to attend and participate in. And a representative of Southwest showed these slides, and I think they're very good. They're instructional, so let me try to tell you what you're looking at here, and you'll be able to better understand that bubbling. Or worse, what happens if you don't see the bubbles, but there's still a fault in the well. Bubbling is bad, but it's not the worst thing that can happen. So this is a cartoon, simplified, of a well with good mechanics. As usual, you have a conductor casing, which has been cemented. You have a surface casing, which has been cemented. And you have a production casing, which might be completely cemented. Notice that this white area, the gray area is cement. The red dots are gas methane molecules. Got the picture here? And the methane molecules are coming up the production casing and going to the surface and being transported to your gas stove. The gray area is cement. Okay, so here's another test. If the scale here is that the diameter of this production casing is on the order of 5 or 6 inches, how thick is the cement?
Depends upon what the diameter of the drill hole is.
Yeah, that's right. Depends upon the difference between the diameter of the drill hole and the diameter of the casing. So if the diameter of the drill hole is 9 inches and the diameter of the casing is 7 inches, how thick is the cement? 1 inch. That's usually what it is, about 1 inch. So in Pennsylvania, there is no requirement that the cement that is injected down the production casing has to go all the way back to the surface. You can have open hole. In other words, this white area is no cement. Okay. Now, if there's no intermediate gas, I'm circling my cursor here, there's no intermediate gas here, that's okay. Nothing is going to come out of the rock, go into that open area, and rise to the surface, and perhaps either be bubbled or captured. There could be shallow producing zones, but as long as you're cementing past them, the gas in them cannot get through the cement if the cement is perfect and stays perfect forever. And so the cement is acting as a good seal. There are a lot of things that can go wrong with that. One is cement channeling. That is, the cement job itself was imperfect initially, and there are various reasons for that. We don't have time to get into tonight, but you can ask me later. Or over time, the cement job fails in some place. In that case, gas from a shallow region or gas from even a deep region can get into the cement area, which is now imperfect, and can migrate along the inside, the outside, or through the cement and rise to the surface. And if the opening of this annulus is sealed, the top of the annulus is sealed, gas pressure builds up in this opening, and that gas pressure could then force gas into the rock formation where it can come into contact with groundwater. Remember that picture? A similar picture can happen, going to the next slide, if the casing leaks. It's steel pipe. How thick is it? An inch? 2 inches? Less than an inch? Significantly less than an inch. Depends upon the diameter. So if that casing for some reason leaks, that is one of the joints leaks, or corrosion eventually causes a corrosion path through the casing, then the casing can leak. And if you have an open annulus, again, gas can come out, go into the annulus. If it's not allowed to vent at the surface, let me go back here. If it's not allowed to vent at the surface, pressure builds up. The pressure can force the gas into the surrounding rock. The gas can migrate into fresh drinking water supplies, your water well. Another possibility, which can happen in Pennsylvania, is that by mistake, the company did not notice that there was a shallow producing zone of gas, and they left part of the annulus open, and so the gas can come out of the shallow formation, go into the open annulus. Again, if this annulus is sealed at the top, pressure builds up, gas migrates into the surrounding rock, can get into surface water. Everybody got those ideas? Those are a number of the things that can go wrong. Remember, the myth we're working on is that what I just showed you is rare. Okay. Let's test that myth by going to industry data. So this is a table taken out of a paper by Brufato and about 10 other authors, published by Schlumberger in their Oil Field Review Journal back in 2003. I'll help you understand this bar chart. The horizontal axis is the age of the wells that were tested for sustained casing pressure. What is sustained casing pressure? Gas got into an annulus by one of the mechanisms I just talked about, or perhaps another mechanism, was not allowed to exit at the top of that annulus, built up pressure in that annulus, and now became potentially available for propagation through the rock formation and into groundwater. That's what sustained casing pressure is. So horizontal axis is age of well. So this is data that was gathered from a large number of wells. And the vertical axis is the percent of those wells that were measured in which there was sustained casing pressure. And the data says the following. When a well is new, roughly 5% of the wells leak. Okay? Is that rare? Well, if you only got one well and 5% of the wells leak, odds are that your well isn't leaking. If you have 20 wells and 5% leak, what are the odds that one of your wells will leak? Pretty good. If you got 100,000 wells and 5% of them initially leak, how many initially leak? Thousands. Okay. Going out to the other extreme, so 28, 29, 30 years, some wells are by the time wells are 30 years old, 50% of them are leaking. How long are the wells in the Marcellus supposed to last? Answer this question correctly. How long are they supposed to last? Wrong answer. The right answer begins with F. Forever. Excuse me, the well is there. When the well goes out of production 5, 10, 15, 20 years from now, they don't erase it. They plug it. And if it's properly plugged, perhaps it's not going to have a problem like this. But now I'm going to show you some other data. Now, I was criticized when I was at the workshop I mentioned a few minutes ago at EPA in Washington because I showed this data. And they said, well, you didn't read the fine print, Professor Ingraffea. This is data from offshore wells. And the guy that criticized me was from Halliburton. And I turned to him and I said, you don't have much to talk about with respect to the structural integrity of offshore wells, especially one that you've been involved with in which over $1 billion was spent. You would expect that that well would be really perfect. So the wells in which you're not spending $1 billion, would you expect them to be less perfect? Never mind.